This video is going to cover a review of sections 2.5 through 7. So transformations, domain, composition and combinations, as well as finding the inverse of a function. Let's go ahead and begin. All right, the first one, we're asked to go ahead and use the graph of the given function to find the transformed function g of x and go ahead and graph that. So again, here's f of x as a function. It passes the vertical line test. And g of x is going to be equal to f of x minus 1. So this minus 1 right here, this is inside the actual function. It's inside the parentheses that defines the input of f. Because it's inside, that means it's going to be some sort of horizontal transformation. And then the fact that it is subtraction means it's going to either be a movement to the left or right. It's going to be a shift. So when we put these two ideas together, remembering that anything with the x, it moves it in the opposite direction, we're going to be moving this to the right one, or it's going to be to the positive direction. So what we'll do is you could just grab some points. So I'm going to just basically take the endpoints and the maximum min and move them all 1 unit to the right. Now the scaling is a little bit weird here. So again, notice everything's by 4. So really the transformation is going to look like so. So let me go and move those anchor points that I'm just using the maximum endpoints. And last one's right here. So again, we'll connect those in the same pattern that was described by the given function. And right there in blue, or my handwriting blue, is the transformed graph. All right, in the next one, we are going to graph the standard quadratic function, which is f of x equal to x squared. So again, maybe just getting ahead, we use these as our anchor points. And if we wanted to go ahead and sketch the graph, it would look something like that. So I'm not going to do that just so it doesn't clutter it. So again, I'm kind of skipping this first part, but do make sure you know your basic functions. This will be a couple of the kind of the low-hanging fruit. Just, hey, given this graph, what is the function? All right, so again, we have our anchor points, and then we're asked to use transformations to graph the given function. So there's two transformations here. Remember to apply them order of operations. This minus 2, it is inside, so it's horizontal. Is subtraction, so it's going to cause it to go to the right 2. Then this negative right here, well, that negative is out in front. So it is going to basically be some sort of vertical transformation. And if you recall, a negative out front is going to make the y's that were positive negative, and vice versa. If there was something negative, it would go positive. So it's going to be a reflection over the x-axis. So let's first apply the movement to the right 2. So the green points will end up, or the anchor points will go there. Then we'll reflect the points that are in the first quadrant down to the fourth. And then we'll go ahead and just sketch a graph in the same pattern as the quadratic function. So there's number 2. All right, and number 3, h of x is equal to x minus 2 squared plus 1. So this minus 2 is going to do the same thing as the previous example. It's going to cause it to go to the right 2. And maybe, again, just to emphasize a little bit change, if this was positive, it would then go to the left. But we'll just do the problem as is. Then this plus 1 is, again, outside, so it's going to be vertical. And then because it's addition, it's going to be either up or down. And outside, things behave exactly like you would expect them to. So this just goes up 1. So my anchor points right here, negative 1, 1, 0, 0, and 1, 1. There's your basic quadratic function. We'll move those points to the right 2, and then we'll go ahead and move them up 1. So that is going to describe the minimum for the quadratic function, which I'll go ahead and graph right there in red. So there's the answer for number 3. On the next page, let's see what we have. Okay, so it's another transformation. This time it is going to be with the square root function. So the square root function, recall, is going to have those 3 points as anchor points. And this time we have that +2, and I alluded to that last time. That is to say, if you have addition inside, it's going to be horizontal. So this one is just going to be a move us to the left 2. So it's going to go to the negative direction, even though it's positive. And this negative right here is going to be outside. So that means, again, it's going to be a reflection, because reflections are caused by multiplication by a negative. And it's going to be a reflection over, again, the x-axis. So let's move the anchor points to the left 2. So it gives us those 3 green points. Reflect anything that's in the upper quadrants, 1 and 2, down to the negative quadrants, 3 and 4. So right there in red, we do have our red graph that is the transformations applied to the square root function. So let's go ahead and, well, before we move on, just as a side note, let's say we had 4b right here, and it was h of x is equal to the square root of minus x. Just to see an example where the negative is inside, this time the negatives are being applied to the x's. So the positive x's, which are over here, will be made negative, so we would have it reflect over here. So this one here is going to be a reflection over the y-axis. And again, just to maybe answer this one would be the one right here in orange. So we'll go ahead and sketch the graph right there. So just wanted to give another example of a reflection, this time in the other direction. So in the case of number 5 and 6, we have the absolute value function. So the anchor points are the same ones as for the parabola, but just remember that this one is going to make a V-shaped graph. It's not going to have that nice curve at the minimum. So here, again, on number 5, we have 3 transformations. So the +4, we've encountered the horizontal shift a few times already. So the +4 is going to cause us to go in the negative direction. So that's going to be left 4. Then we have the negative, which is going to be a reflection. Let's go ahead and just do that in a red. That is going to be a reflection, again, because it's outside, over the x-axis. And then lastly, this +1 is going to cause the graph to shift up 1. Applying them in terms of order of operations, we'll go to the left 4 to move the anchor points over here into the second quadrant. Reflect the ones in quadrant 2 down to the third quadrant, and the one on the x-axis stays where it's at. Again, just because remember the x-coordinate here is 0, and there's, again, some y, negative, excuse me, I have this backwards. The negative 4x, and then 0 on the y, and again, the negative 0 is still 0, so that's why that stays there. And then lastly, what we'll go ahead and do is move them up 1. So that moves the red points right there. And then you just make a absolute value graph, which is this V-shaped graph right there at that maximum. All right. That one's a little off. Let's try that again. There we go. Okay, so the number 6 reintroduces or has this 2, so that's going to be the only difference right here. So let's maybe put that one red, but a lot of the other transformations are still going to be the same. That is to say, we're going to have this +4 right here, and that 4 is going to cause it to move to the left 4. Then the negative 2, you could do this in any order. I'm going to apply the multiplication, which is a vertical stretch. It's outside the absolute value, so it's vertical. And it's multiplication, so it's going to be a stretch. And you could say by a factor of, so I'm going to emphasize by a factor of 2. So just be okay with the language you encounter on the homework. I believe the test has this as a multiple choice question, so make sure you know that multiplication outside is a vertical stretch by a factor of 2. If it is greater than 1, or if you had a proper fraction, it would be a vertical shrink. But the other transformations we still have to apply. This negative right here outside is again going to be reflection over the x-axis. And last but not least, I need a new color here. Let's go ahead and just do, I'm going to use blue as my basic. So we'll do like a purple. So this +1 is going to cause it to go up 1. So our anchor points, again, right here around the origin. We'll go 4 to the left. So we'll have those those points right there. The vertical stretch by a factor of 2 are going to take the ones that are off the x-axis and stretch them upwards. So we have this right here. In the case of the reflection over the x-axis, we're going to go ahead and take those red points that are up in quadrant 1 and move them down, or excuse me, quadrant 2, move them down to quadrant 3. And then we'll also go ahead and just move them again up 1. So again, it's a little cluttered there with points, but our final answer is the one right here in purple. You could compare this even against the one over there on the left. This one you can definitely tell is kind of stretched a little bit. It's not near as wide. All right, so that will resolve the absolute value function and its transformations. Let's go ahead and look at the scenario right here where we have a cubic function. The cubic function, its anchor points are going to be 0, 0, 1, 1, and -1, -1. Again, -1, -1, because if you were to do f of -1, you get -1 cubed, and a multiplication by 3 negatives leaves you at that -1. So the only transformation we have here is this -3 that is inside. So that -3 is inside, so it's going to be horizontal. It's subtraction, so it's going to be a shift, and it's going to move it simply to the right 3. So we'll go ahead and put those 3 points right there, and you could go ahead and sketch it in the shape of the cubic function, which is the one that falls to the left and rises to the right. More on that in chapter 3. So that concludes the review of 2.5. Let's go ahead and look at 2.6. We have 6 examples where asked to find the domain of each function. There's really a couple different cases that we have to work through. So the default case, and maybe I'll go ahead and just put this over here on the right. The default is basically -infinity to +infinity. That is to say, any real number can be plugged in. At this point, the 2 issues we have encountered are with the fractions and radicals. So number 8, it does have this 3 factored out, but again, there's no fraction and radicals, so our domain is simply all real numbers. Any real number could be plugged into this. This right here is going to be a linear function, and you can see that more easily if I distributed that. You can see 3x minus 12 is of the form y equal to mx plus b, y-intercept of -12, slope of 3, and you could graph that if we needed to. In the case of number 9, we do have a fraction. So whenever you have a fraction, what we need to do is see what makes the denominator equal to 0. So I'll just take x minus 4, set that equal to 0. And we find x equal to 4 is the number or the value that must be excluded from the domain. Everything else can be plugged in. Again, if I plugged in 4 here, I would get 3 over 0, which is undefined. But we don't want, that means we can't plug in 4. So our domain is everything else, which is -infinity to 4 with a parentheses. Parentheses meaning don't include 4. And then we use this union symbol, and we go 4 to infinity in order to skip that single value. In the case of number 10, there's no fractions or radicals, so it's -infinity to infinity. 11, we do have a fraction, so I'm going to take the denominator, which is x squared minus 2x minus 15. I'm going to set that equal to 0. Again, remember, the numerator does not, or let me just say it this way, there's nothing even to plug into the numerator, so we don't even have to worry about that. So again, we need the numbers that multiply to -15 but add to -2. Well, again, those numbers are going to be -5 and +3. Multiply them, you get to -15. Add them, you get to minus 2. So the factorization is x minus 2 times x plus 3, and that's still equal to 0. And hopefully you observed at this point, to find what the solutions are, you just go ahead and set, or basically change the sign. So again, it's these two values that must be excluded from the domain. So the domain is everything else. That is to say it is negative infinity to negative 3, union negative 3 to 5, union 5 to infinity. Remember that the negative 3 is smaller than the 5, so we do need to make sure that we keep these intervals ordered. The union allows us, just like above, to skip a particular value. All right, let's go ahead and do 13 first, because it's a little bit, there's less going on. So in the other case we have to remember is whenever you have a square root, what you need to do is take whatever is inside the square root, it's called the radicand, and set that greater than or equal to 0. Again, it's okay to be equal to 0 here, because if you had the square root of 0, that would still be 0. So that 0 is a real number, so it would be an okay output. So here we would just take the 5x plus 35, set that greater than or equal to 0, and let's solve this. So that would be 5x is greater than or equal to minus 35. Again, when you subtract, you don't need to change the inequality. If we divided by a negative, you would. And dividing both sides by 5, you would get x is greater than or equal to minus 7. This right here is the domain. It's just not in interval notation. To do that, we would say negative 7 is the smallest value and x is greater than that. So we would have negative 7 with a bracket to infinity. 12 is kind of that fourth case we've encountered, and it combines the fraction and the radical. So again, we basically say, okay, the square root, we need to make sure that this inside is greater than or equal to 0. But in the case of the denominator, we would have to exclude 0. So all you do here is x minus 3, and you drop the equal to part. So x is greater than positive 3. This right here is our domain. Again, we removed the equal to, so we figured out what we needed to exclude, namely the 3. So the domain here is parentheses 3 to infinity. So those are the main cases for domain you'll want to be comfortable with. All right, in the case of 14, we have combinations of functions. So here, in the case of A, we're asked to find f plus g. So in the case of A, we're just going to take f, which is 2x squared, minus x minus 3. And then you're going to add to that. And again, you may want to put them in parentheses just to watch our signs, although it doesn't make much of a difference for A. So again, you just add to that g, which is going to be x plus 1. So then you combine like terms. So 2x squared. I'm going to drop the parentheses at this next step. So that's minus x minus 3 plus x plus 1. So 2x squared is the only quadratic term, or the only term with the x squared. We have a minus x and a positive x, which end up canceling out. And then minus 3 plus 1 is minus 2. Nothing more to do there. In the case of B, we have a 2x squared minus x minus 3. There's f, and we subtract x minus 1. So here we need to remember to distribute that negative. So we get 2x squared minus x minus 3 minus x plus 1. Combining like terms, we have 2x squared. With this time, both x's are negative, so that's minus 2x. Again, both negative 3 and positive 1 are constant, so that's going to be a minus 2. A little typo here. Let's go ahead and correct that. This should have been a plus 1 based off of what we were given, which would make that a minus 1, which would make this final answer a minus 4. All right, C is multiplication, so let's do that one right here. Just give ourselves some space. In the case of C, we have the f times g, so they're written next to each other, so it's assumed multiplication. So 2x squared minus x minus 3. and then we multiply that by x plus 1. So we just have to do a lot of multiplication here. We do x times 2x squared, x times minus x, and x times minus 3. And then we'll also have to do everything multiplied by 1. So the 2x squared times 1, negative x times 1, and negative 3 times 1. So that's going to give us 2x cubed minus x squared minus 3x. There's the blue part. The green part is just going to give us, let me see here, a positive 2x squared minus x minus 3. And we combine like terms. So we have the x squared terms. So that's 4x. Oh, wait, that's we only have 2x cubed. There's only one cubic term. We have minus x squared and positive 2x squared will just leave us with positive 1x squared. We have the linear terms, which is the ones with just the x. So those are minus 4x. They're both negative, so subtract to keep the variable. And then we just have the minus 3. So that completes C. Nothing more to do there. And lastly, in D, we have to go ahead and divide. In the case of here, in the numerator, we have 2x squared minus 3x plus, we got to have minus x minus 3. And then we divide by an x plus 1. Now, this is one of those things that technically we have divided. So if you just stopped here, that would be fine. Now, one thing I do want to call out, and I believe you encountered this in your homework, is if you could factor the numerator, then you might be able to cancel. So let me zoom into this part and just check what it would look like if we factored the numerator. So using the AC method, we essentially are going to move the 2 with a 3. So x squared minus x minus 6. This factors as an x minus 3 times x plus 2. Again, negative 3 plus 2. They multiplied at negative 6. And then they add to negative 1. If you forgot the AC method, refer back to 1.5, but what we now need to do is divide both sides by the 2. So this is going to be 2x minus 3 as the factorization here, and this is x plus 1. So you can see if we were to keep going, the numerator factors as 2x minus 3 times x plus 1, and we divide this by x plus 1. So the x plus 1s actually end up canceling, and our answer here is just the 2x minus 3. Again, that's just more of a FYI for your information. On the test, you're fine just doing the division. Don't need to simplify that. All right. In the case of 15 and 16, we have composition. There's a little bit of a typo here. In the case of 15, you don't need the parentheses there. I mean, again, that's f of x is just 2 times x or 2x, so we'll typically write that there. I'm going to go ahead and just do 16 as the harder of the two, but I would encourage you to try 15 and then also check your answer there at the end. So again, I'm just going to do 16 right here as the harder of the two, and there's 4 parts. So to do 16, let's go ahead and do 16a. We're asked to find f of g of x. This is the same thing as f and then that circle opening up. And let's do, just to color code things a little bit better, we'll have g of x inside or plugged into f. So what I'm going to do is I'm going to write f, which is 4 times x minus 3, but I'm going to replace the x with a parentheses to which I will go ahead and plug in g, which is the 5x squared minus 2. Distribute the 4 to simplify, so this is 20x squared minus 8 minus 3, and or 20x squared minus 11. Let's go ahead and do 16b now. 16b is just the opposite direction. It's going to be g of f of x. So what we'll do this time is we're going to start with g, which is 5 times x squared minus 2, and we'll plug into that f, which is going to be the 4x minus 3. This one's a little bit more technical because you have to do some multiplication here. So order of operations, you would actually FOIL first. So just to remind you that, it's going to be the 4x minus 3 squared, just a number written or a quantity times itself, bring down the minus 2. Again, you technically could distribute the 5 first, but I'm going to go ahead and just FOIL. So that'll be 5 times 16x minus 12x minus 12x plus 9 plus 2. That's 16x squared. So 5 times 16x squared minus 24x plus 9 plus 2. Okay, multiplication by the 5 here. So that's going to be 80x squared. So let's see, 24 times 5 is going to be minus 120x plus 45 when you distribute there plus 2. So we end up with an 80x squared minus 120x plus 47. That one got a little unwieldy, but not too bad. Part C is just asking, so 16C is f of g of 2. So this 2 right here is an x value. So what we'll go ahead and do is take whatever we got here from the part A, which is f of g of x, and what we're going to go ahead and do is replace the x with 2. So this turns out to be 20 times 2 squared minus 11. And this is going to be 20 times 4 minus 11, which is 80 minus 11, or 69 as our answer. And 16D, which we're asked to do g of f of 2. Again, this 2 right here is an x value. So this one gets a little bit more computationally heavy, so you'll just take whatever you got from that first part and you'll just plug in 2. So this would be 80 times 2 squared minus 120 times 2 plus 47. And again, I don't have a computational device with me right now, but I'll leave that for you to go ahead and verify, and you can check your answer at the end. All right, and let's see what we have next. So in 17, 18, and 19, we're going to talk about inverses. Same with 20 through 23. And then 24 through 26, we actually step back to 2.6. So this one actually what follows the notes next. So let's go ahead and do that. So f plus g of 0. So we have f, and you could, it's not really distributing, but what you could think is that this 0 needs to apply with each of the functions. So it would be f of 0, and then we have to add to that g of 0. So f of 0, you just go to x equal to 0, you look up to the graph, and you notice that you're already at the on the y-axis, so f of 0 is just going to be 2. In the same thought process, g of 0 is going to be 1, so our answer to the first problem is simply going to be 3. In the case of 25, we have to do f of 3, and then we multiply that by g of 3. So f of 3, what you're going to go ahead and do is you're going to go to x equal to 3. You'll find where the graph is, and you'll find that the y value is negative 3. In the same way, you'll go to x equal to 3. And again, I'm focusing right here. It kind of blends in. So let's do it this way. Realize that I'm already on the graph. So I look and I see that the y value is 0. So our answer here is negative 3 times 0, or just 0. Lastly, this last one is a little bit kind of a chase. So this is f, and then remember that f, or that circle, grows into a circle, and inside is g of 5. So what you do is you start with this x value of 5. So let's go right over there. No, let me change up my color just so it sticks out a little bit. So that 5, I go ahead and find g, which is going to be right there, and I look at the y value. So I'm going to replace that minus 5, or excuse me, g of 5 with minus 2. So this is basically a new problem now, where we'll now go back up to negative 2, look at the graph of f, and then we'll go ahead and look at whatever the y value is. So our answer here is just 3. So that completes section 2.6. Let's go back up and look at section 2.7. All right, so in exercises 17 through 19, we're asked to find f of g of x and g of f of x and determine whether each pair of functions of the inverses are inverses of each other. So simply recall that they are inverses. So if f of g of x is equal to, just simplifies to x, and the same thing for the other direction, that is g of f of x is also equal to x, then f and g are inverses. And this could be thought of fairly intuitively, though, as just are operations opposite and in opposite order. That is to say, if you look at f, you can see 3x plus 8. Are the operations taking place in opposite order, and are they opposite operations for g? So notice here we do first times 3, then plus 8. So we want to go ahead and check, do we go in the other order? That is to say, do we first subtract 8 and then divide by 3? And if you look at this, yeah. The the numerator is acting as a type of parentheses. So we first subtract, then we divide. And again, the other function had the opposite operations in opposite order. That is to say, we first multiplied, then we went ahead and added. So intuitively, this is yes. But again, just to verify that, f of g of x is going to be 3 times x plus 8. And we do the x minus 8 divided by 3, g inside. Multiplication comes first, so we end up canceling there. So you have x minus 8 plus 8. And then again, minus 8 plus 8 cancel, so those will go ahead and be inverse x, or those would cancel, so we have all the operations are done. And again, I'll go ahead and leave it for you to verify that g of f of x, a little bit of work, will verify that you also get x. 18 is very similar to 17, kind of in the computation, but again, I'm going to leave it for you to verify the composition. But here, notice here we multiply, then we subtract, but in the g, we're adding, and then we're dividing. So we aren't even doing the opposite operations. Here we're multiplying, the opposite operation is division, so over here we don't divide by 5. So the answer right there is no, and again, you can verify the composition. In the case of 19, this is something also to be aware of, is notice that, again, opposite operations are taking place. So we have minus 4 over here, we add 4. And then we have the cubed root, and over here we cube. So in this case, again, we have the opposite operation, and do they occur in the opposite order? So the first thing we do is we subtract. Is the last thing we do over here add? Yeah. So this is okay. And the same thing with cube and root and cube. That this is going to be, we're going to cube root last, so we need a cube root first here. So intuitively, the answers here are yes. You can verify this just by using the composition f of x, or f of g of x is x, and g of f of x is also x. Again, I'll refer you back to 2.7 notes if you want the details on those. And the last set of exercises simply asks us to find an equation for the inverse and then verify them. Again, I'm going to just worry about A. You won't need to verify these on the test. As long as you do the computations correct, you're going to be okay. I'm going to go ahead and do 21 and 23, and I'll leave for you 20 and 22. All right, so to find the inverse, the first thing that you really need to do, step 0, is check if it is 1-to-1. So that is to say, does this pass the horizontal line test? So basically, does it pass the horizontal line test? And this right here, the given function is just going to be a line that looks something like this. So yes. passes the horizontal line test, so we could find the inverse. So the next thing we'll do, step 1, is you're going to rewrite this as y equal to 2x plus 3. Then the next step, you'll switch x and y. So I'm going to get rid of the numbers right here just so we don't have too much clutter. So let's just do that. So notice x goes here, y goes here, but everything, including the equal to, the 2, and the 3, all stay there where it was. And we solve for y. So we'll subtract 3, so we get x minus 3 is equal to 2y. Dividing by both sides by 2, we get y is equal to x minus 3 over 2. And then this right here is our inverse. That is f inverse, which is x minus 3 divided by 2. And just to do something that involves cube roots, let's look at 23. Again, you can actually graph this, that you're asked, is this 1, 2, 1? Well, if you were to graph this right here, you would just have a shift down 1, you'd have that shape, so it does pass the horizontal line test. Any horizontal line intersects the function's graph at most once, so yes. So we get y is equal to x cubed minus 1. Swap x and y, and you get x is equal to y cubed minus 1. Solve for y, you first subtract or add 1, so you get x plus 1 is equal to y cubed. And then you take the cubed root of both sides. The cubed root undoes the cube. You get y is equal to the cubed root of x plus 1. Again, where this is the actual inverse, so notationally we could say f inverse of x is equal to the cubed root of x plus 1, and we have found the inverse. Again, the remaining two problems are very similar to the ones we just did, but that completes the section, the review for sections 2.5 through 7. I would again encourage you to use this like a practice test. That's to say, redo the problems multiple times until you're comfortably able to complete all of them without referencing any sort of notes or help. Good luck with all of that. And if you have any questions, feel free to reach out. Good luck.